This is video 3 of section 10.3 about polar coordinates. And now we're going to discuss tangents to polar curves. In other words, we're getting to the calculus portion of polar coordinates. So how do we find the derivatives and how do we use those to find tangents or tangent lines? So to find a tangent line, we're going to actually use the parametric representation of the polar equation. So remember, a couple of videos ago, we discussed that if you wanted to translate from r theta, from polar coordinates, into Cartesian coordinates, which are x and y, we can use the formulas x equals r cosine theta and y equals r sine theta. And then if you have an actual equation, a polar curve, r equals f of theta, if you replace the r in both of those formulas with f of theta, then you have a representation in parametric form instead of polar form. And we already learned how to find the derivatives of parametric curves back in section 10.2. So if we use that idea along with the product rule, and we need the product rule because this is a function times cosine theta and a function times sine theta. So remember from the parametric section that dy dx, the derivative of y, can be represented as dy d theta divided by dx d theta. Now in the parametric section, this theta was a t instead, but here our parameter is theta. So dy d theta divided by dx d theta. And then if we use the product rule, with r cosine theta and r sine theta, the derivative of y with respect to theta would be, as a reminder, the product rule is the first times the derivative of the second plus the second times the derivative of the first. So what you see here is the derivative of the first, the r d theta, times the second, plus the first r times the derivative of the second. So the derivative of sine is cosine. And then the bottom is the same idea, only starting with the x equation instead of y. We have the derivative of r times cosine plus r times the derivative of cosine, where the derivative of cosine is negative sine. So this entire equation for dy dx of a polar curve comes from r cosine theta and r sine theta with the product rule. So you don't necessarily need to memorize what you see here on the right if you can remember the derivative of parametric equations and then again the product rule. So how do we find tangents if we know the derivative? Well, technically we have two types of tangents. We have horizontal tangents that come from the derivative of y being 0, and then we have vertical tangents which come from the derivative of x being 0. So we technically have two different types of tangents. And then if we're looking for a tangent line at the pole itself, which as a reminder is the origin, then r has to be 0 or you wouldn't be at the pole. And so the equation 3, which was the equation for the derivative, simplifies down to just tangent theta. Okay, so as an example, when r is cosine of 2 theta, that equals 0 when theta is pi over 4 or 3 pi over 4. This means that those two lines, pi over 4 and 3 pi over 4, are tangent lines to the original polar curve. So that works directly how your knowledge of derivatives already work. You just have to remember that even though what you see here, theta equals pi over 4, makes you think specifically of an angle, it technically is a line in the polar coordinate system because theta equals pi over 4 is an infinite number of points anywhere on the entire polar coordinate system where the angle is pi over 4. And the same thing is true of 3 pi over 4. So pi over 4 would give you a line that looks just like y equals x, and 3 pi over 4 would give you a line that looks just like y equals negative x. So let's look at the example we discussed in the the second video. Remember 1 plus sine theta creates that upside down heart shape that we call a cardioid. So let's use that same polar equation and try to find the slope of the tangent line when theta is pi over 3. And then in part B, they want us to find all the points on the graph itself where the tangent line is horizontal or vertical. So starting out, we need to find the derivative, dy dx. Now remember, our equation is 1 plus sine theta. So here on the left-hand side, you see that equation from a couple of slides ago, just generally what is the equation for the derivative of a polar curve. So what we're going to be doing is replacing dr d theta and r with the specific information from our curve. So r is 1 plus sine theta. So both in the numerator and the denominator, r gets replaced with what it is, 1 plus sine theta. And then what is the derivative of r with respect to theta? What is the derivative of 1 plus sine theta? Well, 1 goes to 0 and sine becomes cosine. So we replace both of dr d thetas with cosine theta, which gives us a long, sort of ugly looking expression for the derivative of y with respect to x of this formula. So the next step would be to simplify as much as possible. On this screen, what you see is the previous equation already simplified a little bit. In the numerator here, we have a cosine in both of the terms, so we can factor it out and we'd be left with sine and 1 plus sine. So that simplifies to 1 plus 2 sine when you factor the numerator. And then in the denominator, we have cosine squared minus sine squared, which using our reduction formulas becomes 1 minus 2 sine squared minus sine. And that is a quadratic that can be factored into 1 plus sine and 1 minus 2 sine. If you replace sine of theta with x, it's a little bit easier to remember how to factor that, but this is basically 1 minus 2x squared minus x. And this is how that quadratic ends up factoring in the denominator here. So if you want to know the slope of the tangent line when theta is pi over 3, we replace all the thetas with pi over 3 and figure out what that gives us. And that is what the simplification at the bottom of the screen is here. We replaced all the thetas in the top formula with pi over 3, simplified all the way down, takes a few steps, and it simplifies all the way down to just -1, which means when theta is pi over 3 on this cardioid graph, the slope of the tangent line there is -1. Now for part B, they want to know all the horizontal and vertical tangents. So we have to observe the dy d theta and dx d theta separately. So dy d theta was the numerator, cosine theta times 1 plus 2 sine, and we want to solve that equal to 0. And that works out to be what you see on the right here. Cosine theta is 0 when theta is pi over 2 and 3 pi over 2. And then 1 plus 2 sine theta is 0 at these other 2 points, 7 pi over 6 and 11 pi over 6. And then dx d theta, which was the denominator of our derivative, 1 plus sine and 1 minus 2 sine, gives us the solutions 3 pi over 2, pi over 6, and 5 pi over 6. So we have horizontal tangents and we have vertical tangents. Remember, the vertical tangents come from dx d theta and the horizontal tangents come from dy d theta. So how do we find these r values that go with the thetas? So for example, pi over 2, that was one of the points where dy d theta is 0. How do I find what the matching r value is? Well, remember that I have a formula for r. R is 1 plus sine theta. So when theta is pi over 2, r is 2. So that's just a plug and play, just as if you had a y equals equation. So the only kicker here is when theta is 3 pi over 2, both dy d theta and dx d theta are 0. They have that theta in common for tangents. So that would create a situation where we need to use L'Hopital's rule, because we would have a 0 divided by a 0. And so using that rule, we end up with infinity, which means there is a vertical tangent at the pole itself. So this final picture is showing everything we just found. Every place you see a horizontal pink line, that corresponded with our horizontal tangents from dy d theta. And everywhere you see a vertical pink line corresponds with our vertical tangents from dx d theta. And then on the top right here, you see the tangent line that, or sorry, the tangent we found when theta is pi over 3. We got a value of -1 for the slope of that tangent line, which you can see represented here on the graph. So this is the original graph we drew in a previous video, along with all the horizontal and vertical tangents, and then the part A that we found, the tangent, the slope of the tangent line to be -1. Okay, so just as a final reminder, instead of remembering the long equation for the derivative, it can help you to remember what the individual representations for x and y are, and then your use of the product rule. So x is r cosine theta always, and y equals r sine theta always. So using the product rule, or going ahead and plugging in r in the beginning, can make the derivative process a lot easier. And this ends the third video for section 10.3.